theorem. Let's now discuss it. First of all, one of the consequences of the theorem is this. The category of abelian spaces localized at isomorphisms of rational cohomology is equivalent to the category of Q-local abelian spaces localized at homotypic equivalences. Now, my claim is we have all machinery to prove this theorem. Except there's one thing which I would like to mention as an exercise. There are two ways which, for all we know, there are two ways to localize, and these are different for all we know at the moment. We can invert homotypic equivalences. This gives us the localization. But another thing we could do is keep the objects and replace continuous maps with homotypic classes of continuous maps. And using the Whitehead theorem, it's not very hard to prove that these two categories are in fact the same. And so this is observation. And using this observation, one can prove, and using what we did last time, one can prove that these two categories are equivalent. Yes, I'm being a bit sloppy when I talk about spaces. There are several categories of spaces which give the same result after we localize. So I'm being a bit sloppy. Yes. So if we one way to proceed would be to consider CW complexes, in which case we need to be careful when we have something like an infinite product, which is not really a CW complex in any meaningful sense. So we need to take a CW approximation. Нет, значит, вопрос в том, а что такое, значит, что мы имеем до локализации. Значит, ответ, что есть несколько вариантов. Вот я сейчас перечислил один.
После локализации там...
Да, значит, после локализации получается то же самое. Вот, значит, что было до локализации? So one option would be to consider CW complexes and continuous maps, and at some point we need to some constructions take us out of this category, in which case we need to realize this and return. Another way would be to consider something which looks like CW complexes, but is better behaved. For example, we could consider simplicial sets or simplicial complexes, and the same remark applies. Some constructions will result in something which is not in the right category, but there is a way to get back inside the category. Значит, если у нас симплициальное множество, то там для них можно там много чего переговорить, значит, но в общем, там язык симплициальных множеств мне не нравится. Значит, он у меня вызывает эстетическое неприятие. Значит, поэтому я предпочитаю what I just said was I personally find simplicial sets aesthetically unsatisfactory, which is why I try to use those as little as possible. And well, it's a matter of taste, and I'm not saying I'm not saying it's anything else. Anyway, there are lots of candidates for a category of spaces, and it doesn't really matter which one we use after we localize. The localized category is the same of equivalence in all cases. Now, is it clear what I'm trying to what the first formula claims? Basically, if it's not clear what this equality says, we'll try to elaborate on it. Otherwise, I would like to leave this as an exercise, because basically we use the general nonsense from the first class to describe the localized category, and then we construct a functor from the top category to the bottom category, and it's this functor is essentially surjective by construction. It's full by construction, and the only thing that needs to be checked is the functor is faithful, which is where we use the description of the localized category from the first class. Okay. Corollary of the localization theorem. There are other localizations. Here, I take rational cohomology. Well, instead of rational cohomology, we could take something else. We could take any other coefficients. And for some coefficients, the construction is exactly the same. Let's first consider the easy case. What is Q? Q is the same as Z localized at 2, 3, at all primes. But instead of all primes, let's see. There is this unfortunate ambiguity. 0 is a prime ideal. So what do we invert when we localize at the prime ideal? We do not invert the elements of the prime ideal. We invert the elements of the complement. And so we invert everything apart from 0, which is the same as inverting all primes. But normally people write R with the lower p to denote the localization in the complement of P. Well, it's annoying, I agree, but this is standard notation in commutative algebra, so we use it. Anyway, to get Q, we need to invert all primes. But instead of inverting all primes, we could invert some of them, and we do get meaningful answers, as we shall see in a moment. Well, the most interesting case is let's invert everything apart from some fixed prime. Then, well, Z with lower s, the localized ring, is the same as the set of all fractions PQ. Q does not contain. Sorry. Let me replace P with R. So R by Q, co-prime. Q. Q does not contain P. Well, this is there aren't any surprises here. Okay, now another way to denote the same thing is to write Z with lower p. What does this mean? This means the same thing. Okay, now now we are able to define localization. And let's just assume that all spaces we consider are abelian unless we explicitly say that this is not the case. A space is ZS local. If and only if all homotopy groups are ZS modules, meaning all elements of all homotopy groups can be uniquely divided by any prime in S, but possibly not other primes. The definition of a localization is the same word for word as in the rational case. A space is a map is a ZS localization if and only if. Firstly, the second space is ZS local, and secondly, the map of the homotopy groups P over star of x tensor ZS to P over star of x prime is an isomorphism. And the theorem and its proof extend word for word. There are literally two places when we need to do something extra in order to handle ZS case as compared with with the case of the rationals. Now, what's the point of all this? Let's recall that every group is determined by its localizations. First of all, what does this mean? Let's denote the localization in the complement of P by G lower P. Then we have the following diagram. And let's let's denote the localization at all primes by G naught. So we have we have the following diagram. It's very simple. All localizations GP map into G naught. Why? Well, because here we invert some almost every prime, and then if we invert the prime itself, we get the localization at 0. Does this diagram make any sense whatsoever? My claim is the limit of this diagram is isomorphic to G. Now, how to prove this? Are there any ideas? By the way, I don't know any proof by general nonsense. I only know how to do this by hand. Does the word limit make any sense? So the first observation is this: if I take G, then the limit of this diagram is, if I take G equals Z, then the limit of this diagram is Z. Let's see. What is the limit of this diagram? it's it's the set of all sequences indexed by the primes, such that the first the element indexed by 2 has by the way, this let's see if this is correct. Does everyone agree with what it says here? I could be wrong, so please pay attention. I want to be able to invert everything apart from, for example, 2. So this means I'm not allowed to have 2 in the denominator. Okay. Now, so this element does not have 2 in the denominator. This element has no 3 in the denominator, and so on. And the images are the same. That's what the limits. They're not allowed to have anything apart from plus or minus 1 in the denominator. Okay, but how to handle an arbitrary group? Are there any ideas? Yes, we could take the tensor product, but there is a problem. Tensor product is it a left adjoint or a right adjoint? Which one is it? The tensor product for groups. Let's fix one argument and consider the tensor product as a function of the other argument. So, left adjoint or right adjoint? Anyone? Так, ну хорошо, Аршак знает ответ, я думаю, но значит, тензорное произведение для абелевой группы. Это левое сопряженное или правое сопряженное? Для абелевой группы. Так, ну, хорошо. Да. So the tensor product is a left adjoint, which is unfortunate. By the why is it unfortunate? We want to be able to say that tensor product commutes with limits. But a left adjoint functor commutes with what? Limits or co-limits? co-limits. So, and in general, left adjoint functor does not commute with limits. So there is no general nonsense argument which would allow us to conclude that this works for arbitrary groups. However, значит, с пределами чего? Где? Значит, home, да, home коммутирует с пределами по какому аргументу? Давайте подумаем. Так, хорошо, а по первому с чем он коммутирует? Ну, если мы его рассматриваем как вот, значит, не обращая ни одной из категорий. Ну, значит, да, значит, переводит по пределу в предел, потому что значит, ко-пределы это то же самое, что пределы, только в противоположной категории. Вот, но сейчас немножко не это интересует. Нас интересует тензорное произведение. So we have this, and we want to prove this. What do we do? Well, there's one again. If anyone knows a proof which follows by general nonsense, please let me know. Otherwise, my suggestion is this. Let's take a resolution of G and well, obviously, tensoring by Z does nothing. Now, let's use the first observation. Z is in fact this limit. So, if we have a resolution tensored by Z, we get basically the same thing. Now, so the first the first step is to consider the case of Z. Then we consider the case of a 3 abelian group, and then using this resolution, we get the result for an arbitrary group. And I suggest we leave this as an exercise because it's I think it's well, I think it's feasible, and we will not really need this statement today. We only want to use this as an illustration. An illustration of what? Every abelian space is okay. Let me also x naught let me use the same notation for spaces as for groups. Then we have the same diagram. Every localization in P maps to the localization in Q. Well, there's a problem. This time we have infinitely many spaces. Which is why the limit on spaces is sketchy. So we need to replace the limit with something else. Instead of just limit, we take the homotopy limit. And the proof is not really difficult. The difficult part is defining this homotopy limit and explaining what its properties are. So this is something we will not do today, but if there are people who would like to see a proof, please let me know. We'll talk about it at some other point. So the localizations, same as for groups, all localizations allow us to reconstruct the space, which is why people who do homotopy theory normally assume from the outset that they will be interested in spaces which are p-local. Q-local spaces are very easy. P-local spaces are less easy, but the behavior is more or less the same for all primes except 2 and 3. 2 and 3 are worse behaved than all other primes for some reason. Fact of life. Anyway, one of the ways to do homotopy theory is to do it one prime at a time. And this diagram tells us why this makes sense. If we're able to reconstruct all localizations, well, then it's in practice. Once we have the localization at something other than 0, it's more or less straightforward to construct this map. And so the all tricky questions in homotopy theory reduce to questions about individual spaces XP. Okay, so we have defined localizations in the localizations of Z, meaning we invert all maps which induce isomorphisms of cohomology with coefficients in some localization of Z. But there are other cohomology theories. One example is the cohomology with coefficients mod p, and in this case there is also a way to construct a localization. To do this, one needs to define something which is related to localization at P, but is slightly different. Namely, one needs the P completion. Again, we will not talk about the P completion today, but if there are people who want to know more, so the P completion and the arithmetic square. So the arithmetic square is something like the black square. It's very powerful and mysterious. If there are people who want to know about it, please let me know. We'll talk about it. But apart from this cohomology theory, there are many other Karl-Malger theories. And there is a way to localize sufficiently nice spaces, basically abelian or nilpotent at the maps which induce an isomorphism of a given Karl-Malger theory, and the name of the procedure is the Bausfield localization. Bausfield or Bausfield. I have no idea how to pronounce this name. Anyway, well, maybe someone else knows, but I don't. Anyway, again, this is not for today, but if there are people who want to know more about this, we'll talk about it in the future. Now, there's one thing which distinguishes the rationalization from all other localizations. The rationalization is algebraizable, and there are at least two ways to do this, and we will today and probably next week we will see how to reduce the homotopy theory of Q local spaces to simple algebra. For other localizations, this is it may be possible, but I don't know the answer. For localizations at something other than 0, it is possible, but more complicated than for localization at 0. So we will start with the rational case, and then once we've seen how the procedure works in this case, we will decide whether or not we want to do something more general. There's good chalk and bad chalk. This one's bad. So we have q-local spaces, and we want to reduce the homotopy theory of those to simple algebra. And to do this, we need, well, there are basically two approaches. One is via CTJs, and the other one is via Lie algebras. And I personally prefer the first one because as we will see today, there is a functor from spaces to CTJs. But there is no easy functor from spaces to Lie algebras. The two approaches are dual, or more precisely causal dual. Okay, now what is a CTG? Well, first of all, what do all the letters mean? A commutative differential graded algebra. Does everyone know the definition? It makes sense to consider those over any ring which is commutative and associative, has an identity, but the category of CTJs is relevant to topology only for those rings which contain Q. If R does not contain Q, then CTJs are not enough. One needs to consider something else. And again, let's talk about it later. If there are people who want to know what happens in those cases. Okay. Now, are there people who would like me to review the definition? No one. Very well. Well, the basic example is is the algebra of differential forms in a smooth manifold. No surprises there. And de Rhams' theorem states that this algebra calculates the cohomology of M with R coefficients. Well, it so happens that this algebra knows a little bit more about M than just cohomology. It knows not the rational, but the real homotopy type of M. We'll see in a minute, or maybe in more than 1 minute, but we will see what this means. Okay. Well, there are more examples of the same kind. For example, we could take the algebra of holomorphic forms on a complex analytic manifold, and this time we don't have the de Rhams theorem on the nose. But there is a way to fix it. Okay, now I want to construct a functor from spaces to CDJs. And to do this, I need to define some sort of forms for in arbitrary spaces. Well, to begin with, let me start with a simplex. The standard simplex, the standard n simplex in Rn plus 1 is, well, again, I think familiar to everyone. If this is not the case, please let me know. Now, next, I want to define differential forms on the simplex. Well, here's what it says: Q polynomial forms. Now, does this expression make sense to everyone? The word polynomial is very important. Why? Well, let's take n equal 1. We can identify 0, 0, 1, delta 1 with 0, 1, and the component A0 will just be the space of polynomials in one variable, and A1 will be the space of one differential forms with polynomial coefficients. I want the integral of this form to be again irrational. In a few minutes, we will see why. If I take something like a rational function here, as we all know, the integral will no longer be a rational number. We could end up with something what number theorists call a period. Basically, one of the way to define periods would be to consider rational functions instead of polynomials. But we don't want any of this at the moment. Although a natural question is whether or not these are related. Okay. Now, once I have defined a once I have defined the forms on the simplex, I want to define the forms on an arbitrary polyhedron. Well, first of all, what's a polyhedron? A polyhedron is the same as the geometric realization of a simplicial complex. Now, does everyone understand what a simplicial complex is? If not, don't keep it to yourself. Please let me know. Now, I have I define A upper star of P for P a polyhedron to be to be the set of collections of forms, one for each simplex, such that the intersections on the restrictions to the intersections agree. Okay, does this definition make any sense? And this definition is definitely a bit weird. For example, if I have something two-dimensional, then in order to define a form in this sense, I only need it on each simplex. There aren't any compatibility conditions. Why? Because all intersections are one-dimensional, and a two-form on something one-dimensional is automatically zero. So it's not obvious that this definition makes any sense. Let's check if it does. Theorem. We have so P a polyhedron. Let P be a polyhedron. Then I have two things. I have A upper star of P and I have C upper star of P with Q coefficients. Now, this is what we've just defined. This is the algebra of singular cochains with Q coefficients. My claim is, by the way, observe that this algebra is definitely not commutative, while this one is. What is QIS? QIS means quasi-isomorphic. What does quasi-isomorphic mean? This means we have a sequence of arrows going in both directions, which connects this algebra and this algebra, and such that every arrow in the sequence is a quasi-isomorphism of algebras. So the sequence may well be very long. Well, in fact, one can reduce the length to 2, but not to 1. Anyway, this is the theorem, and after the break we will prove the theorem. At least that's the plan. Are there any questions? Okay, well, then let's have a break. Так, значит, еще раз напоминаю, что печали закончить. 7. Так, так. Так, значит, по поводу того, чтобы в следующий раз начать раньше. Я разошлю, наверное, сегодня-завтра письмо, и, соответственно, вы в ответ пришлете там возражения, если таковые есть. Okay. So, we have stated the Ram theorem, and well, let's try to prove the theorem. Once again, the first observation is we have two algebras, and one is a genuine CDGA. It's commutative, and the second one is a DGA. It's not C anymore. And so we need to somehow construct a sequence of quasi-isomorphisms which connects the two. Okay, so we question number 1, does the phrase a double complex make any sense? So we have a polyhedron. Polyhedron is made of simplices. Let's take all simplices of all possible dimensions. And let's define APQ to be the direct product. Let's assume that the set is totally ordered. Does this expression make any sense at all?
So is it from I0 or from I1?
This thing is not yes I0. I0. So in in the 0th column, we just have the direct product of the cochains on each individual simplex.
So that does it start from delta I0 or?
So let me draw a picture. So in the 0th column we have the direct product of the chains on all simplices. In the 2nd column we have in the 1st column we have the direct product of the chains on delta I intersected with delta J for I less than J. And so on. And this thing is called the Meyer Vitoris complex. Well, so far we haven't defined the differential, but we have defined all components of the complex.
Again, does we need to start from delta I0?
Oh yes, sorry. Yes, yes, we do need to start from I0. Yes. Okay, now I need to define the differential. Well, since this is a double complex, I need two differentials. Well, firstly, I have the Durham differential, which is basically given by the Durham differential on all components. And secondly, we have the combinatorial differential, which goes from APQ to AP plus 1Q. So it increases the first coordinate. Well, suppose I have an omega inside this group. I want to calculate the combinatorial differential of omega. To calculate the combinatorial differential, I need to specify all its components. The components are one-to-one with indices blah, blah, blah. Well, this thing, this thing lives in AQ of the intersection delta I naught intersected blah 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 intersected delta I b plus 1. I can delete one of these indices. I get a larger intersection. There are fewer indices, so the intersection is larger. I take the form omega, and I take its component, which corresponds to the larger intersection. And I restrict this thing to the smaller intersection. And I insert -1 to the j for good measure. And the claim is delta squared is 0. Well, how to prove this? Well, firstly, there is a straightforward way to check this using the formulas, but it's a bit tedious. So I would like to explain another procedure which is hopefully. Which will help us in a few minutes when we introduce the product. Let me consider the following thing. Actually, I don't want to consider this thing because it's No, let me erase. So I'll explain what this tensor product stands for. But first, let me explain what. No, sorry. Let me keep the notation consistent. Each lambda I is isomorphic to lambda upper star of Q. Well, Q is a vector space, so each vector space has an exterior algebra. Well, this is what this thing stands for. Now, what does tensor roof stand for? Well, it's a graded algebra. It's commutative. Let me just write lambda p. To be the direct product of the vector spaces generated by a formal monomial the product of dx something. So these are formal variables. Question number one, which I don't know the answer to, does this infinite tensor product have a categorical meaning? Arshak, what do you think? Значит, мы хотим определить такую алгебру, которая будет бесконечным тензорным произведением, алгебра лямбда со звездой от Q. Значит, лямбда со звездой от Q это алгебра, то есть так же, как там, внешняя алгебра это алгебра. Вот, а дальше мы хотим определить бесконечное произведение. Значит, результат должен получиться градуированной алгебры следующего сорта. Значит, ее компонента градуировки P, значит, это произведение, а не сумма векторных пространств, порожденных соответствующими мономами. Вот возникает вопрос, а что это? Значит, там значит, как определить такую штуку значит, для произвольного количества, то есть, значит, как определить такую штуку для значит, произвольного набора алгебр? Well, we know that the tensor product is for algebras, not for modules. For algebras, the tensor product is the same as the co-limit of the map from the ground field into both algebras. So let's see. So we have R, the ground ring goes to A1, goes to A2, and the push forward is A1 tensor R A2. Very well. Now well, we could take an arbitrary family of algebras, and we get something, but my suspicion is this something will not be the same as this thing. So first of all, does this definition make any sense? And secondly, is there a categorical way to interpret this construction? And the answer is I don't know. Maybe there is, maybe there isn't. А никакого, ну просто алгебра. Ну, можно сказать, что нулевой. Очень какая странная конструкция, значит, никогда мне не встречалась, вот, но возникает вопрос, а вот будет ли она чем-то таким, то есть, значит, будет ли у нее какая-то категорная интерпретация? Вот, ну, ответ, как я уже говорил, не знаю. Anyway, so we have this algebra which is very big, and we, on the other hand, we can consider it as a DG algebra with the trivial differential. So the next thing is well, let me take the products for all P and Q. APQ. This thing is is a subset of the product. Okay, I want to check delta squared is 0 and to check the Leibniz rule. And to do this, I want to take the direct product of all APQs and embed the result in something which in something which will be a DGA, and then I'll just say that everything will follow from this. There's just one thing I need to think about. Okay. Maybe there are too many products. I'll raise this part. Are there too many products? Okay, let me raise Q and write an asterisk. This way, the result becomes a product of graded objects. Well, a product of CDGAs is a CDGA. So is the tensor product of two CDGAs. And this time we want to just introduce the zero differential on this thing. What's the combinatorial differential? By the way, these are definitely not the same. They are they're different, and this thing is much larger. So the combinatorial differential, which is defined here, is the restriction of a certain map, self map of this space, and namely the multiplication by the sum, quote unquote, of all the differentials of the formal variables. So we have this thing which lives in lambda 1. Here we have lambda p for an arbitrary p, and lambda 1 is just the case when we have just one variable, and this thing lives in lambda 1. Does this make any sense at all? These are formal variables. Значит, я ввожу формальные переменные и завожу такую странную алгебру. Значит, внешнюю алгебру, но значит, в этой внешней алгебре допускаются в каждой градуировке суммы произвольного, значит, в общем, значит, в каждой градуировке стоят прямые произведения. Что за прямые произведения? Прямые произведения, индексированные подмножествами вот такого сорта.
В чем конкретный экзамен получается от x0 или от x1 или 2?
Что?
У нас эта формальная переменная, она как бы одна, да?
Нет, формальные переменные в том же количестве, их имеется, there are as many variables, as many formal variables as there are simplices in our polyhedron P. Сейчас, bad notation, xi. Sorry. Да, значит, сумма всех, ну, то есть такой элемент лямбда-1, значит, у которого все координаты единицы. Ну, в прямой сумме такого нет, а вот в прямом произведении оно есть. Поэтому мы здесь берем произведение. Okay, so by the way, how is this map constructed? We take omega. Omega is a sequence of this type. Where does it go? It goes to and here maybe Okay, so I want to take omega to uh, to an element of this type. Let's see if it makes sense. So first I need to put a tensor product here, and secondly, let's have another look and see if the whole thing makes sense. So what do you think? Ну, для конечных, то есть если полиэдр конечный, то да, значит там все буквально так. Но если полиэдр бесконечный, то у меня есть некоторые подозрения. Давайте подумаем. Значит, что здесь вообще стоит? У меня такое ощущение, что все это очень подозрительно. Да, ну, собственно, проблема в том, что значит, как описать, значит, здесь прямое произведение, здесь прямое произведение. А что такое тензорное произведение двух прямых произведений? So let's so we have a direct product and another direct product, and we want to tensor multiply two direct products. Okay, now a question to everyone. Does the tensor product commute with arbitrary direct products for vector spaces? In other words, suppose we have V alpha tensor W beta on the one hand, and on the other hand, we have P V alpha beta of V alpha W beta. How are these two things related? What do you think? Where alpha, V alpha and W beta are just some vector spaces.
Ну, обычно у нас есть только списки снизу вверх, видим, скажем, когда все ветры пространства одномерны. Сейчас. Мне кажется, конечно, как-то вообще изоморфизм.
Ну, да, мы сейчас рассматриваем тот случай, когда у нас количество вот этих бесконечно.
Да, я понимаю, но как-то один изоморфизм у нас есть всегда. Непонятно, селекцию непонятно, когда ожидать.
Значит, в какую сторону? Do we have a natural map from upstairs to downstairs, or the other way around?
From up to down, because up is point, down limit.
Okay, so from upstairs to downstairs, we by the definition of the tensor product, we have a bilinear map from the product of all these to the product. Do we?
Ну да, то есть нам нужно просто. Ну да, конечно, у нас сверху сейчас.
Mystery.
У нас сверху и вот возьмем сверху унитарный тензор, да, то есть просто элемент произведения и элемент произведения от того, да. И мы можем их, вот мы их проецируем. Ну да, то есть стрелку куда это надо тензор отправить? Стрелка вниз произведения, это стрелка какой-то из компонент. Ну, вот мы отправляем просто тензор в компоненте, который это пара.
So what Arshak is saying that suppose we have an element of here, tensor, an element from here, and each of each of these of the tensor factors has an alpha component and a beta component, and so we take the result the tensor product to the sequence of the alpha component of the first one tensor, the beta component of the second one. So indeed, we have an arrow from upstairs to downstairs, but is this map injective, surjective, both, neither? It's surjective because, well, suppose we have an arbitrary element from here. What is it?
Мы при всех v альфа имеем один точку, как бы, ну, у нас там при v альфа мы можем только, как бы, можно я напишу на схему?
Да, конечно.
Ну, я вижу, что все они отсюда.
Мгм.
Вот это примета сверху, да? И когда мы эту операцию выполняем, у нас при вот этих вылетах у нас при всех флешах у нас там только конечное число q возникает, понимаете? То есть у нас там вылитая тензор quit, оно отправляется оно здесь отправляется в вот этот кортеж. То есть quit, тензор. У нас мы можем при всех v мы конечное число q можем брать. Здесь мы можем при каждом выбрать свое. Мы можем взять элементарный тензор каждой компоненте, и то есть эта штука намного больше, чем это, видимо.
Ну хорошо, да. Значит, иначе говоря, давайте рассмотрим случай, когда все они одномерные.
Я тоже в этом случае думал, но мне показалось, что в этом случае как раз все одинаково, потому что когда они все одномерные, это все R тоже, да, и таблица получается просто произведение q в степени.
Да, значит, let's
Да, правильно.
We need to finish, but let me just explain what happens when all spaces are one-dimensional. Then the in this case, the product of V alpha would be map NQ. And the same for the product of W beta, but the product for alpha and beta would be the same as map n squared q. Not every map from n squared to q is a finite linear combination of something which depends on the first coordinate times something which depends on the second coordinate. Does this make sense? Okay, so anyway, let's the product of the product times the product is a subset of the product of the products. Okay, we need to finish now. So let's and I haven't thought the proof through properly. So we'll continue next time.